Good morning, everyone. Welcome to the latest instalment of the Reality of Net Zero seminar series. My name is Paul Shearing. I'm Director of the ZERO Institute for Zero Carbon Energy Research at the University of Oxford. And today I'm going to be doing a double act with my colleague, Professor Dave Howey, and we are going to be talking about battery energy storage and low carbon grids, and thinking about how energy storage plays a key role in our journey towards net zero in a really broad range of applications, from transport to grid scale energy storage, both locally here in the UK, but also internationally, as we build a resilient net zero energy ecosystem. So before we sort of start, I thought that I would first of all thank the organisers at Oxford Net Zero for their organisation of this brilliant seminar series, and also just take the opportunity of a bit of a captive audience to tell you all a bit about the ZERO Institute, which is a sister initiative for the Oxford Net Zero initiative here at the University of Oxford, where we are focused on the zero carbon energy system. We were founded back in 2022, around about the same time as Oxford Net Zero, and our goals are to establish Oxford as a centre for thought leadership on the zero carbon energy transition, and to really promote the university's world-leading research across disciplines and provide a bit of a focal point for zero carbon energy research in partnership with the Oxford Energy Network. Now, the way that we organise ourselves in the ZERO Institute is around 5 key technology domains. They are in zero carbon energy generation, zero carbon energy conversion, distribution, storage, and use. And we have a number of foundational capabilities. And our vision collectively is that we want to shape the transition to a just and fair global zero carbon energy system through research that unifies technology, policy, and people. And as I mentioned, a core part of our philosophy is to embrace the multidisciplinary strengths across the university. We're hosted by the Departments of Engineering, Geography, and Materials, but we reach into all 4 corners of the world-leading multidisciplinary research, engagement, and teaching activities across Oxford. And as we will talk about in significant detail through the course of this morning's seminar, we're going to be exploring the role of energy storage in the zero carbon energy system, with a particular focus on the role of batteries. I mentioned that we work very closely with the Oxford Energy Network, and would invite you all to look at the Oxford Energy Network website, which flags a number of the activities that are coming up in coming weeks and months, building towards Oxford Energy Day, which is going to happen, as always, in September this year. In addition to the core activities of the ZERO Institute, I also wanted to flag some activities that we're doing to support climate tech entrepreneurialism through our ZERO Institute Founders Network, where we are looking to support the community of entrepreneurs in translating climate tech from lab to market. And obviously that's a core part in the journey towards net zero, is getting things from the university lab and into real world deployment. And the lithium-ion battery that we'll talk about over the course of this morning's seminar is a really brilliant example of how that has had really global impact from foundational research that was conducted here in Oxford in the 1970s. And so, with those sort of very brief adverts completed, I wanted now to sort of switch gears and talk about the content of today's seminar in the context of the UN Sustainable Development Goals. Now, all of you, I'm sure, will be very familiar with the UN SDGs, and obviously in the context of the zero carbon energy system, one that I'm keen to highlight is number 7, which is clean energy. And of course, the symbiosis of all of these SDGs together really give us the trajectory towards achieving global just sustainable development. And I would just flag that if we don't manage to achieve clean energy through renewable energy supply, but also through energy storage, then actually we jeopardize really almost all of the other SDGs as well. So actually pursuing the zero carbon energy system is absolutely central to achieving the goals of the wider SDG portfolio. And if we just for a moment take a sort of view of the UK and the greenhouse gas emissions by sector from back in 2020, we can see that as we map these by percentage of greenhouse gas emissions for that year of 2020, we can see that we've got 2 major culprits in terms of the significant emitting sectors. They are in transport and energy supply. Somewhere around about the mid-2010s, transport overtook energy supply as the most emitting sector in the UK. And that recognises, of course, the significant efforts that were made over the past 20 years or so in deploying renewable energy generation in the UK, particularly through offshore wind, but also through onshore wind and solar. And there's been a really substantial reduction in the emissions from the energy supply sector as a consequence of that. And of course, many of us will celebrate the fact that in October last year, the UK decommissioned its last coal-fired power station. But as a consequence, we now see that transport is the most emitting sector. And so when we think about the role of energy storage, actually we're thinking about batteries, for example, for electric vehicles. We're also thinking about batteries for the grid. And if we want to build a resilient, renewable, zero carbon energy system, being able to have energy storage embedded within that energy ecosystem is absolutely critical to provide mobile decarbonised power, but also to provide the resilience that's required for a zero carbon renewable centric grid. And as well as batteries for electric vehicles and batteries for the grid, we might also think about what other funky applications we can think of for energy storage. So even things like batteries for electric flight, and maybe even really large batteries that could provide long duration storage alongside a range of different technologies. So we'll touch upon all of those over the course of the next sort of half an hour or so from myself and also from my colleague Dave Howey. But if I just begin with the role of energy storage in the grid, you can see that we have a bit of a triumvirate between renewable generation, the electricity system, and battery storage. And the video that you can see, I hope, playing on the screen is a screenshot that I took from the Tesla website about 18 months or so ago, which I think really just illustrates how the battery energy storage have become a really commoditized product. You can see that over the course of that video, you can literally go to the Tesla website. You can select where you want your battery to be. You can select how large you want it to be. There's multi-megawatt hour batteries that you can buy. And actually, you can just click your credit card, and with Apple Pay, you can say, yep, I'm going to pay a deposit on this really large grid scale energy storage asset. And so with the commoditization of battery energy storage, you can see that in the UK on the right-hand side, there has been an enormous growth in the installed capacity for energy storage, and that continues to grow substantially alongside our renewable energy generation portfolio. And the main way that these battery energy storage devices are currently operating is through the lithium-ion battery. And here in Oxford, as I mentioned, we're very proud of the lithium-ion battery because actually next door to where I'm sitting here in the geography department today is the inorganic chemistry lab, where in the 1970s, John Goodenough and his co-workers discovered the lithium cobalt oxide cathode material that then became the building block for all of the generations pretty much of lithium-ion batteries that have subsequently followed. And along with Stan Whittingham and Yukiro Ishino, they were awarded the Nobel Prize back in 2019 for their work. And I think it's a wonderful illustration of how we can really drive world-leading fundamental research, but also the translation to real-world deployment that has obviously completely revolutionized consumer electronics and electric vehicles, and is now poised to play a very substantial role in the decarbonisation of the energy grid. And of course, this is a very multidisciplinary team. We're delighted that actually Stan Whittingham was an undergraduate here in Oxford. John Goodenough was chair in inorganic chemistry, but they work very closely with the Sony Corporation to commercialise that, and the multidisciplinary team that were awarded the Nobel Prize back in 2019, I think really embody the multidisciplinary principles that are required in order to take world-leading technologies and deliver real-world impact and deployment. Here in the UK, over the course of the last 7 years, we've been very closely working with the Faraday Challenge and the Faraday Institution in framing what the technical targets for energy storage should look like. And actually, internationally, most countries have a roadmap that looks somewhat similar to this. We need batteries for a really broad range of applications, perhaps starting with electric vehicles, but moving towards grid-scale energy storage, and a whole host of other applications, which may also include electric flight. And in order to achieve that, we need batteries that are cheaper, but also batteries that can store more energy. They can deliver it more quickly with higher power densities. They operate over wide temperature windows with high predictability, good recyclability, and of course, inherent safety. And so those technology targets are really framing what it is that we're trying to achieve with the current generation of lithium-ion batteries, but also framing what it is that we might look to achieve with next generation post-lithium-ion chemistries. If we look at the pathway to commercialization for the lithium-ion battery as an example of many materials innovations, we can see that actually it's quite a long and drawn-out process. The lithium cobalt oxide cathode material that was discovered in Oxford back in the late 1970s really took a bit more than a decade to see commercial deployment, and perhaps more than 30 years before we really got to the productivity of the current generation of lithium-ion batteries and the era of the gigafactory. And of course, it was 40 years from discovery to the award of the Nobel Prize in 2019. So it is a long journey. And I think this is important to bear in mind, that we really need to accelerate our research translation activities, because let's face it, in the journey towards net zero by 2050, we don't have time on our side. And being able to accelerate the commercial deployment of the technologies we're currently researching in the labs is absolutely critical if we're going to make a dent on achieving net zero by 2050. I mentioned electric vehicles as one of the framings for the benchmarks that we have conceived for battery performance. But actually, you can see that across a really broad range of different batteries, we can find different applications, from extremely high power batteries that may operate, for example, in supercars, to extremely high energy density batteries that are going to be required for the electrification of flight. It's almost the case that we can matchmake the batteries with different characteristics to a whole host of different applications, and being able to walk the tightrope between the energy that a battery can store, the power that it can deliver, and navigating our way across the periodic table to identify the sustainable critical materials that are needed is absolutely a key challenge that the battery community here in Oxford and beyond is trying to address. But of course, some of this is not particularly new. Batteries have been around in different guises for well over 150 years. And in fact, even the electrification of the automotive sector is not a new idea. At the turn of the 20th century, if you were going to buy a vehicle, there's about a 50-50 chance that you might buy a combustion vehicle or you might buy an electric vehicle. And in 1900, Charles Rolls, the founder of Rolls-Royce, said the electric car is noiseless and clean. There's no smell or vibration. It should be very serviceable. And he was really a pioneer of motivating for electric vehicles. Now, of course, it took an awful long time for that to become a reality. It was 123 years later that Rolls-Royce launched the Spectre, which is their current generation of electric vehicle. And so again, we can see that it takes a long time for these concepts to become reality. And in the context of achieving net zero, there's a huge acceleration that's required. We are lucky that here in the UK, there is a huge groundswell of activity, not just in basic research, but also in translation. And we can see some news stories from the course of the last few years. Jaguar Land Rover are building a gigafactory down in Somerset. Right here in Oxford, BMW have indicated that they intend to pursue electric mini production in South Oxford in Cowley. And so there's a huge amount of industrial activity that will enable, we hope, the translation and the real-world deployment from lab to market. And it's not just the OEMs. There's a huge amount of activity from small and medium-sized enterprises, often ideas that were seeded here in the university sector being translated to real-world deployment. But for anyone who's been watching the news recently, no one said it was going to be easy. And of course, there's been a massive shock from Sweden in recent months with the situation at Northvolt, one of Europe's leading battery developers who are having very significant financial challenges. And again, close to home, the BMW have indicated over the course of the last week that there are some uncertainties to the electrification plans for the BMW Mini Oxford plant. And so actually, as we journey from a combustion-based automotive sector towards an electric vehicle sector, it is a rocky ride, and we need to, I think, have the courage of our convictions when it comes to being able to ride out that roller coaster of electrification for electric vehicles, but also for the deployment of large-scale energy storage for our grid. And there are some things that are becoming possible because of the next generation of lithium-ion batteries that really, even as a battery scientist and engineer, I find really, truly remarkable. And they include really ambitious plans for the electrification of really tough to decarbonize sectors, like, for example, the electrification of flight. And the video that you can see is from Vertical Aerospace, who are a UK-based startup company who are building electric powered eVTOLs, vertical takeoff and landing vehicles, powered by lithium-ion batteries. So again, there's a huge range of applications where these building blocks of the lithium-ion battery can be used in our pursuit of net zero. And there's a good reason why we are sort of championing the lithium-ion battery, not just because it was invented here in Oxford, but because it does represent a wonderful technology in terms of the balance of power it can deliver and energy that it can store. The graph that you can see here is what we call a Ragone plot, which has the power capabilities on one axis and the energy capabilities on the other axis. And you can see that lithium-ion batteries are really pretty high performance in both energy and power domains. And that means that they lend themselves to a really broad range of applications. But the fundamental building blocks, whether you're building an electric vehicle or a mobile phone battery, are really very, very similar. We have a negative electrode. Normally that's made out of graphite. Graphite can intercalate or store lithium ions during charge. And then during discharge, we have what's described as a rocking chair phenomena. So the lithium leaves the negative electrode and moves back to the positive electrode, and it cycles as a lithium ion between the negative and positive electrodes many hundreds or thousands of times as that battery is charged and discharged. And it was the discovery of these materials and devices that led to the Nobel Prize in 2019 that I've already mentioned. I'm going to, in the next couple of slides, talk a little bit about some jargon. So I thought it was worthwhile just framing exactly what I mean there. I think everyone will be familiar with the voltage, the potential difference that a battery can offer. For a lithium-ion battery, that's normally about 4.2 volts. And you will probably also be familiar, if you look at the back of your mobile phone battery, it will give you a capacity in amp hours. And actually, if we take the voltage and the capacity and we multiply them by each other, that provides the watt hours or the energy that can be stored in a battery. And that's about all the jargon that I'm going to use. But the reason for going into that jargon is because I think that actually just from our day-to-day lives, we can identify, using those common building blocks of lithium-ion batteries, a really broad church of different applications, from the sublime to the ridiculous, in terms of how we use lithium-ion batteries and how we will continue to use them in our pursuit for net zero. So if we take a single lithium-ion battery, and this is from a small toy drone, this is about a 1 watt-hour battery. It's about a 250 milliamp hour, 4-volt battery. That gives us about 1 watt-hours. And that's enough to power a toy drone that you might buy for a Christmas stocking filler. If we take about 40 of those batteries, it's big enough to power my vacuum cleaner. If we take about 500 of those batteries, it's big enough to power my bike. And it's important to note that the fundamental chemical building blocks of all of these different applications are exactly the same. And we can extend that much, much further. If we look, for example, a passenger electric vehicle, the Jaguar I-Pace, has about a 90 kilowatt-hour battery. So that's equivalent to 90,000 toy drones. And actually, at the really largest end of the scale, we can see things like the Tesla Megapack, which routinely install batteries that are more than 100 megawatt hours, or 100 million of those drone batteries in one installation. That's a really important feature in providing resilient and secure renewable energy supply. And again, all using those same fundamental building blocks. But if we were to look inside the black box of what is inside a battery, what's it actually made out of? Well, I won't go into huge detail here, but a teardown analysis from a Generation 1 Nissan Leaf car reveals that we've got all manner of different materials and minerals in there. We've got natural graphite and copper, the negative electrode. We've got a transition-based oxide material in the positive electrode. We've got liquid electrolytes, and they're all packaged together in a really neat black box that we kind of take for granted. But as we'll see in a few slides' time, the pressures on the supply chain that are emerging as we scale the battery industry to really unprecedented scale are beginning to show, and that's beginning to reveal some pressures and geopolitical issues in terms of how it is that we design the battery of the future. But one thing that was missing from that diagram was anything about metallic lithium. Although we talk about the lithium-ion battery, and of course there are lithium components in there, there is no metallic lithium in the batteries that power our cars or the batteries that power our phones. And one of the reasons for this is because lithium is a spectacularly difficult metal to handle. As you can see from this video from YouTube, and this definitely comes with a health warning not to try this at home, lithium is extraordinarily reactive. Now, I would would not motivate that this is a particularly scientific experiment that our YouTube friends have delivered, but it does illustrate exactly how reactive lithium metal can be, and really motivates for us to think very carefully about how we're sourcing the materials and designing the devices for high energy density energy storage moving forward. But what is inside a battery? It's about, if we break this down by cost, it's about 50% cost is down to the positive electrode, about 25% of the cost is down to manufacturing. The anode's a bit cheaper, the separators, the cell casing, all build up to that picture that a cell today, or rather in 2021, costs on average about $100 per kilowatt hour. And this is spectacularly cheap. Over the course of the last decade, and we've seen even further price reductions since 2021, we've seen about an order of magnitude reduction in the cost of battery energy storage. And as a consequence, there has been, and we'll see in a bit more detail in a few slides' time, a very significant growth in both the demand and the manufacturing capacity for lithium-ion batteries. And we project that by 2030, the demand is going to be around about 5 terawatt hours of lithium-ion battery storage that will be manufactured. And that comes with some significant challenges. If only we consider the supply chains that I mentioned, we're going to need an awful lot more lithium, but we're also going to need the cobalt, the nickel, the natural graphite that go into the composite electrodes that make up our lithium-ion batteries. And if we translate that to the number of mines that are needed internationally, we think that we probably need about 80 new lithium mines just to service the 2035 demand for lithium-ion batteries alone. And so therein lies a significant challenge, because if we look to the EU's critical materials list, and perhaps we can plot that on a periodic table instead to be a bit more digestible, you can see that a number of the materials that I've mentioned, the lithium, the carbon, the cobalt, the nickel, the copper, all of the things that go into the black box of our lithium-ion battery are actually often represented in the critical materials list for the EU, for the UK, and for many other countries. And you can see I flagged here the transition metals, the carbon, the lithium that we rely upon for our lithium-ion battery energy storage. And these are critical materials that are not geographically evenly distributed. You can see, for example, that an awful lot of the world's cobalt comes from the Democratic Republic of Congo. Similarly, China have a huge share of the world's natural graphite processing capability. And so with the growth of a global supply chain, we also have to pass that with the critical materials and the uneven geographical distribution of those critical materials. We see a similar point when we think not just about the raw materials, but also the manufacturing capability. This is what the 2021 lithium-ion battery manufacturing capacity looks like by country. And we see a significant concentration of manufacturing activity in China. But even as Western Europe and North America grow its lithium-ion battery capacity, we'll see that actually we still, by 2025, have an outsized proportion of batteries being manufactured in China. And by 2030, again, an enormous growth in the global industry, but one that remains very highly dominated by China moving forwards. And this is also constrained by the not only the availability, but also the volatility in pricing for the raw materials. And so you can see that nickel, which is a fundamental part of the lithium-ion batteries that power our cell phones, actually has had an enormously volatile few years in terms of its pricing. And the ebb and flow of the commodities industry is naturally changing the supply chain dynamics globally. And so this leads us not only to think about what lithium-ion batteries might do, but also what the next generation of sustainably sourced batteries might look like. And we've seen in recent years a huge renaissance in lithium iron phosphate as an alternative cell chemistry, which has perhaps a more sustainable supply chain. But even beyond this, when we begin to think of post-lithium ion chemistries like lithium sulfur, like lithium air, like sodium ion batteries, we see a spectrum of opportunities to develop and deploy a range of different battery chemistries in the pursuit of net zero. And so whilst there is a huge imperative to manufacture more lithium-ion batteries and to deploy them in a range of different applications, I would also argue that there is a huge portfolio of different battery chemistries available, and we have an opportunity here to really matchmake the best battery with the best application. And so I thought that I would close before handing over to Dave with just a couple of case studies that indicate those building blocks of lithium-ion batteries and how we can scale them from very, very small applications up to extraordinarily large ones. And the first one is a case study that we did on disposable vape batteries. So e-cigarette batteries, even the disposable ones often contain rechargeable lithium-ion batteries. And about 1.3 million of these batteries are discarded, often just by the side of the road, regrettably, in the UK. But if we consider those 1.3 million rechargeable lithium-ion batteries that are disposed of every week in the UK alone, how many Teslas could we make every year from discarded UK vape batteries? Well, I'll tell you, it's about 2,000 or more than 5 million iPhones. So again, those building blocks that go in from everything from e-cigarettes all the way up to electric vehicles. The critical material stewardship is really important so we can guarantee the security of the supply chains and motivate for a circular economy for lithium-ion batteries. If we take a step up, if we think about, again, the Nissan Leaf battery, you can see the generation Nissan Leaf battery in the image in the top left of the screen. Each vehicle from the Nissan Leaf Generation 1 vehicle contained about 192 individual cells. And if we think about a grid-scale energy storage battery, the Roscoot battery is one example that's in the northeast of England. It's 25 megawatt hours. Now, one key sort of philosophy in the circular economy for batteries is that just because a battery is no longer suitable for an electric vehicle application, maybe it will be good in a second life application for grid scale energy storage. So how many end-of-life Nissan Leaf vehicles would it take to build a Roscoot energy storage battery? Well, it's about 1,300 cars worth. And when you think about the domestic production of electric vehicles, that's not very much. And so therein lies a huge opportunity to establish an end-of-life or second-life trajectory for automotive batteries that could be used in a grid-scale energy storage application after they finish automotive service. The third case study is the Tesla Megapack. The Victoria Big Battery is in the southern Australian province, and it is about 450 megawatt hours. It's one of the world's largest batteries, but it's likely constructed from those exact same building blocks that go into Tesla Model 3s, and they're called 21700 cells. They're 21 millimeters in diameter, and they're 700 millimeters high. Oh, sorry, 70 millimeters high. So by a rough back-of-the-envelope calculation, how many individual cells make up the big battery? Well, it's about 27 million. So in my example earlier, I said that we could take 90,000 toy drones and we can make an electric vehicle, but actually we can take 27 million cells and make up one enormous grid-scale battery like the Victoria Big Battery that we can see here. And so you maybe sort of fall into thinking that actually lithium-ion batteries are a silver bullet and all of our grid services, our energy storage needs will be met by lithium-ion batteries alone. But I'm here to dispel that myth because energy storage using lithium-ion batteries has to sit alongside a much broader church of energy storage options. Because back in 2022, a number of us, led by Chris Llewellyn-Smith, authored a report for the Royal Society on long-duration storage in the UK. And one of the upper estimates was that the UK could require up to 120 terawatt hours of energy storage. Now, on the right-hand side of this, you can see an image from the Financial Times, which shows us what the global production of lithium-ion batteries was from 2020 projected out to 2026. So related to the top 5 battery manufacturers, if we wanted to build a large enough battery just to service the long-duration energy storage needs of the UK, how many years of production does this equate to? Well, it's about 100 years worth. And so clearly we need some alternative energy storage mechanisms. The lithium-ion battery, whilst it's a technology that is phenomenally versatile, is not going to be a silver bullet for all of our energy storage needs. And therefore, when we're thinking about the future of zero carbon energy grids, we have to consider the decarbonisation of energy generation in partnership with a really broad portfolio of energy storage options. And at that point, I will pause and hand over to Dave, who I think is going to talk to us more about the opportunities for grid-scale energy storage in the global context. Thanks, Dave. I will move it over to you.
Thanks very much. Right, just 10 seconds of laptop orchestration here. So just get that. Great. All right, we're on. Well, hi, everyone, and thanks very much, Paul, for that incredible overview of both the opportunity and the challenge, I think, that we face. So what I'm going to do, and I'll keep it relatively short, is give an overview of a more specific piece of research that we've been doing over the past several years on the performance of batteries in small off-grid solar systems in Africa. And I should say this is, of course, a big team effort, and just to name, you can see some of the names of the other people on the slide who are involved here. I will quickly give you an overview of what we do in my group, but I think Paul has done a very good job of giving you the big picture, so I'm going to skip through some of this. But in Oxford, we have a large amount of battery research ongoing across many departments. In my group specifically, we're interested in modeling and control of batteries from an engineering perspective. So not so much from the materials chemistry, but more how do we get the most out of the commercially available batteries that we can buy. And these pictures give you a flavor of that. So you can see some modeling activities here, but also some diagnostics and testing in the lab. And we have a spin-out company called Brill Power that is actively pursuing commercialization of some of these efforts. But what I want to talk about now is energy access, and specifically providing small off-grid systems to people predominantly in countries such as DRC, we've just mentioned earlier, but also Kenya, Rwanda, and various parts of sub-Saharan Africa. And just to give you a flavor of what we're talking about, these systems you can see in the picture here are around 50 watt hours. So it's, I guess, this sort of size of the vacuum cleaner from Paul's earlier example. And we've had an ongoing program of research with a really exciting company called Bbox, which was started about 15 years ago by 3 graduates from Imperial College. And Bbox make these small systems. They are used for lighting, phone charging, radio, TV, but they have a whole host of other things going on, extending into clean cooking and e-mobility, for example. They have probably upwards of almost 1 million of these systems in the field, and these systems provide a rich source of data for us to look at both battery performance, but also how people use energy. Just to give you a feel for that, here's what happens if you log into the sort of back office, Bbox's kind of platform, and you can see, for example, the data from one of the systems might look like this, and you can see very detailed information about currents and voltages and temperatures and so on. And that's, of course, a treasure trove of useful stuff for a researcher like myself who's interested in how batteries age and behave in the field. So how we make use of that data, let's have a quick look at that. I'll first just briefly talk about why I think battery health is important. If you have an electric car, then you can see here, this is actually a picture of my electric car. You might be concerned about how much will your car be worth in 5 years' time when you try to sell it. If you have a large grid battery, Paul mentioned these earlier, then you'd be concerned about questions relating to return on investment, for example, at the project planning stage. And if you're an off-grid system supplier like Bbox, then it's a logistics challenge. How many spare batteries should you order to replace ones that are failing? And all of these questions require us to have a good understanding, a good prediction of how long the battery is going to last under different usage conditions in the field. And these are actually quite difficult challenges because if we take a battery and put it in the lab and test it in a certain way, we don't always know that those test results are going to be entirely comparable with what we see in the field. So we have to use data and models to kind of come up with good predictions. And the kinds of models we might consider, just to give you 2 extremes. On one extreme, we've got models where we try to recreate all of the sort of different physical and chemical processes in the battery. Just to show you an example, this is the so-called DFN or Newman model, which is derived from porous electrode theory. You can see a simulation here of concentrations and potentials and things inside one layer of one small section of a cell. And, we can postulate that maybe there's a certain mechanism for degradation, and we can build a kind of battery simulator that allows us to do virtual testing and aging of cells. And actually, there's a huge amount of effort in modeling going on in this right now. And if you're interested in these topics, have a look at the software called PyBAM, which is an open source modeling tool for this. But there are lots of challenges around how you parameterize these models, challenges about what the mechanisms actually are, and so on. So at the other extreme, there's a lot of interest also in machine learning or data-driven approaches. Of course, this is a huge topic. At the moment, lots of hype around machine learning in general. And this is a topic which we've done lots of research on. We can do things like, for example, predicting the health of a battery from data or predicting the future life. But I think one of the challenges in the battery space is that actually we don't always have particularly good, rich data sets, and it's quite hard to generalize. So for example, you can see in this picture here how we might have state of health. So that's kind of the size of the tank, the size of the battery capacity decreasing over time. We might train a model on one set of data, but then test it at slightly different conditions, maybe a different temperature or something, and then the model fails to predict at the new conditions. So this is a kind of ongoing issue which just says we need more data. And so we've been looking at using field data to kind of increase the amount of data we have and the richness. And what we've been doing is building a system to suck up data from these BBox off-grid solar systems. The kind of data we get is voltage, current, and temperature. And then we fit those using a very, very simple equivalent circuit model. And we actually, in the first instance, we use the resistance as a kind of health metric. And we have to calibrate that because it's sensitive to temperature and state of charge and so on. And then we can, from that, kind of build a machine learning pipeline which tells us whether we've got a healthy or a failing battery just based on the field data without having to switch it off and do extra tests. Here's an example of this kind of fitting process. You can see the voltage at the top and then various different views of the resistance along the bottom as a function of concentration and current and temperature and so on. The point of this is that we have to do this in order to kind of calibrate these measurements accurately to make them comparable, because otherwise we're not doing apples to apples comparisons. But we've developed this and run it against more than 1,000 batteries from the BBox data set. And what typically happens with these batteries is that the ones that fail, they have a resistance that kind of starts to increase very sharply, okay? And you can see here, the ones that fail are colored in red, the ones that are healthy are colored in blue. And if we combine this metric with some aging factors, such as calendar time that the battery's been in the field and how many cycles it's done, we can actually build a classification system that is about 20% more accurate than the sort of baseline comparison that we were using. So you could think, by analogy, it's a little bit like testing for COVID. There's a certain background prevalence, and you go and you do a test, and the test kind of amplifies that, and that's kind of a little bit of what's going on here. So that's what these equations are about. Very happy to send them to you if you want more detail. And the end result is we can say to the technician, well, the probability of failure is quite high for this number of batteries this month, so you should order that number. And we also get more understanding into what's actually causing aging. Okay, for the last 2 minutes, I'm just going to talk about how, so I'm going to zoom out a little bit from battery health and just talk about how people actually use energy in these systems, which is an important and relatively underexplored topic. So the end goal here, I think, is to say, once you've understood how a battery ages, how could you actually make decisions to extend the life and make best use of it? And one of the things we've noticed is that people use these solar home systems differently. And there's 4 examples here. So you can see there's a case where people use it quite a lot. There's kind of moderate use, infrequent use, and there's low use, which essentially means it's kind of off. And we wanted to try and understand a bit more about what was going on in these cases, and then propose some different kind of mechanisms for controlling the battery so that we could try to extend the life. In this case, we propose a very simple kind of control, which is just to change the maximum voltage that the battery charges to. And in this particular battery chemistry, this is not actually lithium ion, this is old-fashioned lead acid, but we can also do something very similar on lithium ion. In this particular chemistry, there's a trade-off between 2 different degradation mechanisms. So if you spend a lot of time at high voltage, you get a lot of aging caused by corrosion. But if you go to low voltage, you get a different mechanism. And so you somehow need a trade-off between these 2. And what we've been doing is doing field tests with BBox to try and understand how, if we modify these maximum voltages for charging in the field, how can that extend life? And to help with this, we've been using clustering techniques to basically look at energy use. One of the challenges with clustering time series data is that it doesn't line up always very nicely. And so there's a technique which we use called dynamic time warping, which allows us to compare time series which might be misaligned but otherwise similar. And if we do that on the BBox data, we end up finding around 5 major kind of usage clusters. And these vary from single and double peak throughout the day. So here we're seeing hours of the day on the x-axis and then power on the y-axis. And we can see distinctive patterns. So at nighttime, we have this kind of U-shaped pattern in usage compared to the moderate usage, where it's basically off in the day and then used in the evening. We also have this low usage pattern, which I mentioned earlier, which is basically the system is turned off. And this is from a huge data set, by the way, of more than 1,000 customers. This kind of data in the UK context is kind of widely understood. If you connect a new house to the electricity grid, it's quite easy to size the wires because there's information available about how much people use. But in these off-grid contexts, this is not so well understood. So it's useful to look at real data. One of the things that we found curious in this data set is that actually people's consumption of electricity over time tends to decrease. And interestingly enough, this is not only for financial reasons. So these are pay-as-you-go systems. People tend to pay per day or per week. If they don't pay, the system gets switched off. But even if we remove these so-called economic outages, basically the consumption still decreases, and it still decreases irrespective of whether they are sort of high energy users or low energy users, with some slight differences between them. And honestly, we don't fully understand why this is yet. It may be caused by a similar phenomenon to when you or I get a new piece of equipment and use it really intensively for the first few weeks and then kind of relax a bit. Or it may be some other thing that we don't yet understand. So this is kind of source of ongoing research. Okay, just to summarize, so we're still learning how batteries perform in the wild. Often the data we get from lab tests doesn't always compare well to field data, so we need to do more field work. If we combine aging models with the ways that different people use batteries, for example, if I'm a taxi driver, I'm going to drive my electric car much more heavily than if I'm me, for example, then that's really important for understanding life. And this is also true for larger systems. You know, Paul painted a picture of how big some of these systems can be. I have a battery in my house. Here's a home battery. The home battery might charge up to 100% and then sit at 100% for a large amount of the day, just because of the control strategy. And actually, this could be quite detrimental for health. So there's simple things we can do, simple control strategies to extend life. Yes, we've looked at energy use in these solar home systems as well. We found that it tends to decrease around 20–30% over time, and we're still doing some work to understand why that is. Okay, so lots of exciting stuff, lots of things coming on in the future. We're doing more work to try and prove out these ideas in the field. We're really interested in the growth of lithium iron phosphate, LFP, and Paul and myself and others are working on a larger project on circular economy and second life issues that he mentioned as well. Okay, so with that, I will stop, and I think we've got sort of 15-ish minutes for questions. Thanks. Want to join me? Yeah, actually, sorry, before we do that, we should say that there is a seminar next week, and there are details on this website, netzeroclimate.org, and I think it is the last seminar for this term. Yeah, so please do join us. Great. Right, we're just going to have a look at the questions.
Okay, so thanks for everyone who's put questions into the Q&A function. Do continue to add those. You can also upvote questions as well. So the first one, does storage as a source of resilience require European production for security of supply? Right. Well, very good question. Thanks, Alex, for that. I mean, I think that as we saw, and we whizzed through the slides very quickly, but at the moment we do have a massive centralization of lithium-ion battery production in China, and actually that's projected to grow even further. So there will be almost, semi-monopoly sort of in certain cell chemistries and their manufacture based on China. I'm not an expert in sort of geopolitical relationships, and nor would I pretend to be, but I do think that there are some anxieties around the security of supply when it is so dominated by a single region. I think that this is also part of the reason that we see increasing motivation for a broader geographical distribution of the sort of gigafactory ecosystem. And you will have seen the relative growth of gigafactory growth in North America and in Northern and Western Europe to be quite significant from some of those graphs. But it's also worthwhile mentioning as well that this is not easy. Actually, sort of standing up a gigafactory is an activity that takes billions of euros and, probably the best part of a decade. And so there is a case that the UK, Europe, North America is somewhat playing catch up in that space. But we're pleased that in the UK, for example, there are commitments for at least 2 gigafactories that will largely service the electric vehicle sector. And I think that will help to provide a bit more distribution and perhaps resilience in the supply chain as well.
Yeah, I mean, it's also worth noticing just how deep the sort of supply chain is towards the gigafactory. So, you have to get the materials processed, and many of those predecessor steps before the materials get to the factory where the battery is made are also located in one region of the world. So I think, yeah, there is some concern about it, but
I think this also means that we have to sort of really interrogate the full life cycle of the battery, because actually we, mine the materials internationally, and there are again some bottlenecks in terms of supply there. They end up sort of traversing the globe really as they're sort of processed and then deployed in cell manufacturing facilities and ultimately end up in a device. So I think there is an increasing interrogation, and rightly so, of the embedded carbon within that process as well. And Paul Begley mentions in the Q&A as well around the sort of geopolitics of lithium batteries looking complicated, and perhaps one solution to this is in next generation chemistry. So sodium is a really good example. I mean, Dave, what's your take in terms of the role that sodium-ion batteries might play in the next 5 to 10 years, and maybe begin to disrupt some of those supply chain tensions?
Yeah, sure. So I think sodium-ion is very interesting. I think if you look at the characteristics of sodium-ion in terms of as a battery, it's probably sort of similar to lithium iron phosphate on one level. So there's a bit of competition there, and LFP obviously has a head start. So we have to consider that sodium ion is further back in the kind of scale up and rollout. That said, there's a lot of activity in India. There's also a lot of activity in China for sodium. Sodium is sort of a drop-in technology in the sense that it's made in a similar way to lithium ion. You're just swapping some of the materials. So I think it's interesting, it's exciting, but in some ways the challenge is going to be quite similar to lithium, the geopolitical challenges. But there's, I guess, more diversity of sodium available. But,
I think
it's not the only material.
Three orders of magnitude, I think, more sodium than there is lithium, so it is substantially more available. But I mean, we still have transition metals in the sodium-ion battery cathode, which might suffer from some of those supply chain constraints as well. So another question about vehicle to grid integration. Do we have any projections for what the rough percentage of total storage that could be covered starting in the UK by vehicle to grid? I think just for everyone's context, the notion of vehicle to grid integration is that when we have a even higher penetration of electric vehicles, we can all drive home at night, plug our cars in, and we have something called bi-directional charging, which means that we accept electricity from the grid to charge up our batteries when there is a surplus of power being generated. But actually, when there's a deficit, you keep your car plugged in and you can provide grid services that will enable to sort of buffer any shortages in supply. And actually, you see increasingly vehicles are equipped with this bi-directional charging. To give some context, a normal electric vehicle has a battery of about 50 kilowatt hours. And that's probably about 5 times the size of the battery that's in your house, Dave. So there is some significant scope for vehicle to grid balancing. I don't think we've really exercised that as much as we could to date. Do you think we're going to go down that path?
So I absolutely think it's a good resource. And I think it's sort of a no-brainer if you can make it work practically, because it doesn't make sense, given that many people's cars sit on their drive most of the time, to have another battery in your house. I used to be a skeptic in terms of battery aging, but I think actually if you're only using the middle 20% of your car battery capacity, it's not a big deal. I think the challenge for vehicle to grid is actually the practical aspect of how do you get the back office counting and all the communications and stuff working distributed across millions of customers. But I think it's in principle a very good idea.
Great, thank you. Just looking through the kind of Q&A, and if folks want to upvote things, that will help Dave and I to triage which one we're going to answer next. We'll take Kath's one next, which is what do you think is needed in the university sector, government and industry to accelerate the commercialization of new battery technologies, and how much that is in place at the moment? So, I mean, I think that one thing that we hope to do through the Zero Institute Founders Network, and also working with lots of partners around the University of Oxford and more broadly, is to provide a bit more of a sort of entrepreneurial culture, because there is no shortage of brilliant science going on, and there are some really great examples of that science being translated into real world deployment. And Dave, I'll come to you in a sec, because I know that you've got a lot of personal hands-on experience in that. I think that it will be great to do more entrepreneurial training for our undergraduates, our postgraduates, our early career researchers, because I think that there is an increasing recognition, actually, that if we want to turn the needle on our contributions to net zero, it's wonderful to carry on doing groundbreaking fundamental research, but actually one pathway to achieving genuine impact is through translating that either to industry or to spin-outs. So Dave, you were involved in a handful of spin-outs, but perhaps most notably, you mentioned brittle power in your slides as well. I mean, what are your experiences there, and any ideas about how we can do things to accelerate that journey even faster?
Yeah, so Brittle Power is a company that is commercializing a sort of modular battery system with more granular control of aging. I think some quick observations. So, I mean, hardware is difficult. I think it takes longer to do stuff where you're making actual things. I think the spin-out process from the university is improving and has improved, and there's still a way to go, I think, in the UK. I'll just say that at this stage, but the direction of travel is good. I think there are lots of great opportunities and competitions and venture competitions and things. I think sort of getting people on the coalface of understanding that you need a customer to pay you in the end as early as possible, maybe undergrad is great, and so there's a huge amount of opportunity and network around Oxford to improve that even further.
Okay, we've got a question from Ed about alternative energy storage, and then we've got a few questions about data. So Ed asks, are you working on alternative energy storage methods to batteries, so flywheels, thermal? I think the short answer is absolutely yes, and I perhaps briefly touched upon that when we consider the long duration energy storage challenge. I mentioned that if we want to store the upper limit of the UK's estimation for interseasonal energy storage, we need about 100 years of global lithium-ion battery production. And so that means that we absolutely need technologies beyond batteries. Often we sort of sort these by time constant. So how long are you going to store the energy for? And if it's seconds, you might find technologies like flywheels, like the current, that might displace some of the spinning reserves that are currently utilized in gas-burning power stations. In the sort of duration of hours, we probably find technologies principally dominated by batteries. But beyond sort of tens of hours, or perhaps 10, 12 hours, beyond diurnal storage, I think that there are a really broad church of different technologies available, from pumped hydro to compressed air to flow batteries, and at really large scales to hydrogen. And we absolutely need to navigate all of those different time constants, from perhaps even millisecond frequency generation through to month or even annual, maybe even decadal energy storage. So batteries are not going to answer all of those questions, and having a portfolio approach, I think, is really important.
All right, so
should we talk about data? There's been a few questions there about data. I mean, a lot of that stems in one sense from the availability of data. And you've obviously got some close industry partnerships where you've been able to get your hands-on real-world service data. Is there more that needs to be done there? Do you find it a big bottleneck?
Yes, and yes. And I mean, it makes such a huge difference to be able to get your hands on real world data in this context. We've been extremely lucky to have worked with BBOX for a decade or more. I think someone mentions Octopus Net Zero Center here. Absolutely, Octopus are a good example of a very data-centric company. I think, if anyone out there has battery field data and wants to share it with us, I'd be delighted to take a look. And we've got algorithms we could throw at it straight away. Yeah.
And I think Alex mentions as well, so 7 gigawatt hours of installed grid scale storage capacity here in the UK.
Yeah.
And I think maybe a request,
Yeah, I can talk
Dave,
about
from
that.
you. If people have got data, you're a very willing
Yeah.
recipient.
So what I think one of the issues with battery data, specifically on the grid storage side, is just there's a lot of it. Obviously, Paul mentioned 100 million, drone batteries in one of these Tesla megapacks, for example. And so data in itself is great, but actually you need to be quite careful to decide what level of data you're looking at and what level of abstraction. And often the companies who are controlling these large grid batteries are not getting access to the kind of detailed cell data. Maybe they don't want it, or maybe it's kind of filtered in a way that is unhelpful, for example. So I think disconnect between the various layers of people interested in data is a problem, and also a lack of kind of standardization and consistency. We have a way to go on that, I think.
Great. Thank you, everyone. And do continue to sort of upvote questions so we can see how we're doing. Anik asks, Pakistan is currently importing massive solar power equipment from China, and because of that, the main grid is facing severe outages. At this scale, I wonder how national policy can be shaped in terms of recycling huge volumes of battery materials in the coming 10 to 15 years. So I think that when we think about outages, whether they're driven by technology changes or whether they're driven by geopolitical changes, or in the case of renewables, as we can to some degree predict, will always be the case, whether they're driven by changes just in weather patterns. Part of the key to buffering those changes is through energy storage. I mean, very obviously, and Dave, from your experience with BBox, obviously, this speaks to the challenge of diurnal energy storage, because you're only generating solar power when the sun's shining, but you want to boil the kettle when it's dark. You still need some storage capacity. Yes, there are definitely challenges from outages of different flavors, and I think that I would say that in general, energy storage is the way in which we can begin to sort of ride out the kind of uncertainties.
Yeah, I think it's an ongoing question. I mean, I don't know about the specifics in Pakistan, but the ongoing question lots of people at the systems level have is, how can you make a clean, cheap, secure system? And there are some tensions there. I think the world is coming to accept that solar, for example, is in many places the cheapest source of power right now, and certainly will be in most of the world very shortly. But the variability of solar output is a challenge, and how you come up with a system that gives you the consistency you need at the least price is a challenge. Yeah.
I'll try and cluster a couple of questions just in the closing minutes of the seminar. So Juan has asked if the case study around interseasonal storage is available. Absolutely. If you Google Royal Society large-scale electricity storage, you'll find a white paper from 2022, which has all of the detail in terms of the projections for what the UK's interseasonal energy storage is. And in that, it speaks to a range of different technologies, a number of which have come up in different questions in the Q&A. So batteries form part of the energy storage puzzle, but at interseasonal durations, it will be a case that batteries are probably not going to be able to economically store battery at that scale and at that level of throughput. And so we need alternative technologies, pumped hydro being one of them, large-scale hydrogen storage being another. People have talked about the Swiss Energy Vault, which is a sort of form of gravitational energy storage. I think that there is a portfolio of options, and actually in the medium to long duration storage, there will be some geographic constraints in terms of how they're deployed. So I suspect we'll see a sort of portfolio approach in different countries and different regions of the world. But we absolutely, I think, need more basic underpinning research to begin to interrogate the technology solutions for medium and long duration storage.
I think we're running short on time, but maybe I'll just quickly pick up this question about electricity usage and people's behavior, which relates to the stuff I was presenting. The question or the suggestion basically is that, maybe you need more sociology, anthropology, and user input. Absolutely agree with that. And 100%, there's limits on what we can do just with simple engineering data. And so, yeah, we want to get that data as well, get that qualitative survey kind of input.
Yeah, I mean, and across the university, I can think of sort of things like EDOL, the Energy Demand Observatory and Laboratory, which is, I think, combining both technical and social inputs into
Yeah.
understanding the sort of energy
Yeah.
usage and portfolios with a view to
Yeah.
then intelligent demand side reduction as well. I think that we are just about out of time. What we'll try and do is gather up all the questions that we've not managed to answer and see if we can ping some responses over to everyone. I think we'll close by thanking everyone for coming, for all of those really engaged and well-informed questions, and by flagging that the final seminar in this current series is happening at, I believe, midday next week, and all the details, as always, on the webinar. So with that, we will sign off and say thanks ever so much.
Thank you.